Welcome back, AP Chemistry students, to Unit 4 Chemical Reactions. Today we'll be talking about Unit 4.4 Types of Chemical Reactions. Now, in first year chem, we go over 5 different types of chemical reactions. However, in AP chemistry, we say there are only 3 types of chemical reactions. Now, the reason for this is that just like in biology, where there's different ways of classifying organisms, whether there's 5 kingdoms or 6 kingdoms, in chemistry there are different ways of classifying chemical reactions, either by a pattern that exists, that's what you learned in first year chemistry, or by the overall outcome of the reaction, which is what we go over in AP. However, it is fair for you to know both types of reactions, so let's quickly review what you learned in first year chem. In first year chem, we talked about the 5 different types of reactions, those being synthesis or combination, when I have 2 or more reactants that form one large product. So, for example, the Haber process, nitrogen and hydrogen making ammonia, or the combustion of hydrogen making water. 2 or more reactants making one large product is a synthesis or combination reaction. A decomposition reaction is the opposite, where one large reactant decomposes into 2 or more reactants. So the Haber process run in reverse, or potassium chlorate decomposing into potassium chloride and oxygen gas would be another example. Decomposition reactions run opposite of combination or synthesis reactions. Next are single replacement reactions, when something elemental replaces something in a compound. So, for example, hydrochloric acid and reacts with fluorine gas to make hydrofluoric acid, and chlorine gas would be an example of an anion single replacement reaction. Cation single replacement reactions can happen as well, like if magnesium metal is added to hydrochloric acid, you produce hydrogen gas and magnesium chloride. These are single replacement reactions. Something elemental replaces something else in a reaction. A double displacement reaction is what we've seen in all of our precipitation things we've talked about, where 2 compounds, their anions and cations switch. So some compound reacts with another to produce some different set of compounds. And again, we've talked about this with our precipitation reactions, right? So like lead nitrate reacting with potassium iodide, producing insoluble lead iodide and the spectator ions potassium nitrate. Lastly, a combustion reaction is when oxygen produces 1 or more oxides, things that end in oxygen. So the classic example is when a hydrocarbon reacts with oxygen to produce carbon dioxide and water. However, there is some overlap. For example, hydrogen gas combusts to produce water. That's a combustion reaction where oxygen produces 1 or more oxides. In AP chemistry, we talk about just 3 types of reactions: precipitation reactions, redox reactions, and acid-base reactions. Precipitation reactions is what we've talked about at the beginning of this unit. So you have to know your solubility rules. And when a salt is insoluble, you can filter it and dry it in order to determine how much stuff is present. So precipitation reactions are your first one to know. So example 18 is an example of a precipitation reaction. Sodium chloride reacting with silver nitrate to precipitate out silver chloride. If we want to know how much sodium chloride to add to our silver chloride to get all of the silver out of solution, We'll first write a precipitation reaction where silver nitrate reacts with sodium chloride to give us the insoluble salt silver chloride and the spectator ions of sodium nitrate. A double displacement reaction or a precipitation reaction as we form an insoluble salt. And then it's just a simple stoichiometry problem. We want to know what mass of sodium chloride is needed to get all of the silver out of our silver nitrate. In order to figure out how much sodium chloride we need to figure out how many moles of silver are present of those silver ions. Now, when you have molarity, which is the number of moles for each liter, if you take molarity and you multiply by volume, that'll tell you how many moles of silver nitrate you have. So, 1.5 times 0.1 would tell me that I end up with 0.15 moles of silver nitrate. For every 1 silver nitrate, I need 1 sodium chloride to get my silver chloride. So I can set up my mole to mole ratio and convert from silver nitrate to sodium chloride to figure out how much sodium chloride needs to go with it. And since it's 1-to-1, I need 0.15 moles of sodium chloride. However, I need to know what mass I need. So I need to convert from moles to grams. Remember, we use our molar masses. So sodium chloride would be 1 sodium and 1 chloride for a molar mass of 58 grams for every 1 mole. So multiplying all this out, we would need 8.77 grams of sodium chloride in order to precipitate out all of the silver. So precipitation reactions use all the stuff we've talked about up to now: net ionic equations, solutions. The second type of reaction in AP chemistry are known as acid-base reactions. When an acid, which will simplify the formula as hydrogen and some anion, reacts with a base, which would be some cation and a hydroxide ion, neutralize one another. Now, this is a simplified version of acid-base chemistry. We have an entire unit to talk about acid-base chemistry later in the year. However, a brief introduction to acid-base chemistry here is that acids and bases together form water and some salt. Now, the water comes from the fact that the acid will donate hydrogens to solution and the base will donate hydroxides. So all acid-base reactions produce water and then some salt, some cation and anion. Now, since all acid-base reactions produce the same products, we can use this information to determine how much acid or base is present in something by slowly reacting them through a process known as titration. Titration mixes an acid and a base with the objective to get your moles of acid to equal your moles of base to neutralize the solution. Now, in a titration, we use a burette, which is kind of like an upside down graduated cylinder where it goes from 0 to 50 usually. You open it slowly through the stopcock, which is a little nozzle at the bottom of the burette. And drop by drop, you can mix these two solutions together. You're looking for them to neutralize one another, and you'll know they've neutralized one another when an indicator changes color. Indicators change color in the presence of either an acid or a base. Acid-base reactions are fairly simple to balance if you remember that water can be rewritten as hydrogen hydroxide, HOH, because that HOH will tell you where the hydrogens from your acid went and the hydroxides from your base went. And then it's a matter of simple balancing. I have 3 hydrogens, 1 phosphate, 1 potassium, and 1 hydroxide. That becomes 1 hydrogen, 1 phosphate, 3 potassiums, and 1 hydroxide. So to balance this, I will need 3 waters to give me the 3 hydrogens I started with, but that'll also give me 3 hydroxides. 1 phosphate balances 1 phosphate. 3 potassiums cannot come from 1 potassium, so putting a 3 in front of the molecule with potassium will give me my 3 potassiums, but it also triples my hydroxide, and just like that, the reaction is balanced with the coefficients of 1 to 3 to 3 to 1. So again, remember that acid-base reactions always produce water and some salt. So water, which can be rewritten as hydrogen hydroxide. The hydrogen from water comes from the acid. The hydroxide comes from the base. Now with that little hint, let's see if you can balance number 19. Please pause the video and try number 19, letter B. You only needed to put a 2 in front of water to give you 2 hydrogens and 2 hydroxides that you started with. So the coefficients being 1 to 1 to 2 to 1. Acids are classified, much like ionic compounds, as being either strong or weak, depending on how they behave when placed in solution. A strong acid, when placed in solution, completely dissociates, and there are only 6 strong acids. They are nitric, sulfuric, and perchloric, and then the halides, with the exception of fluoride. So nitric acid, sulfuric acid, perchloric acid, hydrochloric, hydrobromic, and hydroiodic acid are the only 6 strong acids. When you place these in solution, every single one produces the maximum amount of hydrogen ions and anions. And therefore they are a strong conductor of electricity, so we label them as strong acids. The reason that they are strong deals with what they are paired with. Hydrogen does not have a very high electronegativity, so when paired with things that are very electronegative, electron hogs, those electron hogs, those electronegativity values, pull the electrons away from hydrogen, making it easily attracted to other molecules, specifically water. So the greater the electron density in the anion, the stronger the acid tends to be. This is why perchloric acid is strong. It has a massive electron density due to the number of oxygens, whereas hypochlorite does not have as strong of an electronegativity pull on the hydrogen's electrons. Bases are similar. A strong base, a strong conductor of electricity. Strong bases also dissociate completely, and there are only two strong bases you need to know. Those are group 1 and group 2 metal hydroxides. So any metal cation from groups 1 and 2 hydroxides we will label as strong bases, with the exception of magnesium and beryllium, but this is such a small exception that typically the AP exam avoids it. But just for your edification, magnesium and beryllium are not really considered strong bases because they mostly dissociate, but they don't completely dissociate. Therefore, they would land in the weak category. Weak acids and weak bases only partially dissociate into solutions. So something like hydrofluoric acid is a weak acid. Most hydrofluoric molecules stay together because fluorine holds that proton, that hydrogen ion, very close to it. A few hydrogen ions do break free, but they are usually less than 1%. If less than 1% of a substance dissociates, we classify it as weak. So a weak acid or a weak base, less than 1% dissociate in solution. We will dive more into all the fun that goes with strong versus weak acids and bases when we get to the acid-base unit. For right now, just this precursory understanding is enough to get through. That understanding being that there are 6 strong acids: hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, and sulfuric acids. And there are only a handful of strong bases. Those are group 1 and 2 hydroxides. Everything else is considered a weak acid or a weak base. Now, whether you have a strong acid or a weak acid, a strong base or a weak base, when the two come together, the acid will give off hydrogens, the base will give off hydroxides, and together they will produce water. So the two neutralize one another, they limit their effects when the moles of acid equal the moles of base. And they'll also equal the moles of salt produced, but no one's ever particularly interested in the salt, at least not until we get to hydrolysis. When we carry out a titration, we know the moles of acid equal the moles of base when we see a color change. That color change indicates that there has been a switch from being an acid to being a base. Now, different indicators have different color changes, and they don't all change at the same place. Litmus paper is the one you are probably most familiar with, learning about in biology, right? Red litmus paper turns blue in a base. Blue litmus paper turns red in an acid. When the moles of hydrogen equal the moles of hydroxide in water at room temperature, phenolphthalein will switch from being colorless in an acid to being pink in solution. So when it's just faintly pink, that tells us that we have something very near neutral. But other indicators change at different values. And it deals with those moles of salt for why you would use them. The other two indicators here, methyl orange and methyl blue, you would use based off of that salt. The salt produced in solution is not neutral. It can favor one side or another. And in the acid-base unit, we will talk about which side they favor. But methyl orange and methyl blue are used for when a salt is going to favor the base side or when it favors the acid side. And when we get to that unit, we will go into more detail about how you pick which one to use in solution. For right now, just knowing they exist is enough to make you dangerous. So we carry out titrations in order to determine the molarity of an acid or the molarity of a base based on the fact that when the moles of acid equals the moles of base, the solution is neutralized. So if we take the molarity times the volume, we can end up with the number of moles. All this problem is saying is that the moles of acid have to equal the moles of base. So it's the equation that we will use when we do titration problems. When we react an acid with a base and we want to know how much it takes to neutralize one or the other, we'll use molarity times volume of the acid equals the molarity times the volume of the base, keeping in mind that some bases have more than one hydroxide to give, and some acids have more than one hydrogen to donate. So we will need to keep track of that. So let's learn by doing. Let's try example 20 in your packet. It takes 45 milliliters of 1 molar sodium hydroxide to neutralize 57 milliliters of hydrochloric acid. What is the concentration of the hydrochloric acid? So the number of hydrogens times the molarity of the acid times the volume of the acid will give us the molarity of the base times the volume of the base times the number of hydroxides. If we want the molarity of the acid by itself, we will need to divide by the number of hydrogens and the volume of the acid on both sides. So the molarity of our acid is going to equal the molarity and volume of our base times the number of hydroxides divided by the number of hydrogens times the volume of the acid. So we have a volume of the base, we've got the molarity of the base and its formula. We know the volume of the acid and the formula of the acid. So now it's just a matter of plug and chug. The molarity of the acid is going to be the molarity of the base, 1 molar, times the volume of the base, 45 milliliters, times the number of hydroxides, which there is 1 hydroxide in sodium hydroxide, divided by the volume of the acid, 57 milliliters, times the number of hydrogens, and there is 1 hydrogen in hydrochloric acid. And as long as your units of volume are the same, this problem will work. So the molarity of our acid turns out to be 0.789 molar. If it takes 45 milliliters of 1 molar sodium hydroxide to neutralize 57 milliliters of sulfuric acid, what is the concentration of the sulfuric acid? Again, we know the volume, molarity, and identity of our base. We know the volume of the acid and its formula. And we are asked for the molarity again, but this is going to come out different, even though all the numbers are exactly the same, because sulfuric acid is diprotic. It has 2 hydrogens it can give off. So when we plug and chug, our number of hydrogens this time is 2. So the molarity of sulfuric acid here is half as much. Now, as we add our acid to our base, or we add a base to our acid, the pH, the amount of hydrogen present, will change. We can show this on a titration curve, where as we add our titrant to solution, the pH will shift. So if we start with something at a low pH, as we add our titrant to it, as those hydrogen ions pick up the hydroxide ions, they will begin to rise. The pH goes up until our moles of acid equals our moles of base, known as the equivalency point. Traditionally, a strong acid and a strong base, or a weak acid and a weak base, will give you an equivalency point near a pH of 7. However, a strong with a weak, in either case, will change that. And again, we will go into much greater detail in later units. But with that being said, in your packet, you can do page 29. Remember, the moles of acid times the volume of the acid times the number of hydrogens has to equal the moles of base times the volume of the base times the number of hydroxides in the formula. Alright, if you don't know the names or formulas of things, feel free to ask or to look them up. But I expect you to do page 29. Before I loose you on page 29, one final note. I told you there were 3 types of reactions: precipitation reactions, acid-base reactions. Lastly was redox reactions, and redox is short for reduction and oxidation. Reduction is when an atom gains electrons. Reduction is a gain. Oxidation is when an atom loses electrons. So personally, I remember it as oil rig. Oxidation is a loss, and reduction is a gain of electrons. You can remember it also as Leo the lion goes grr. You need to know that oxidation is when an atom gains electrons. So in our previous units, when we talked about how fluorine with 7 valence electrons could gain an electron to become the fluoride anion, reduction is a gain. Fluorine is reduced, therefore. Now, where that electron comes from is typically a metal. So, for example, sodium has 1 valence electron. If it lost that 1 electron, it would be isoelectronic to neon and become a +1 cation. Sodium, therefore, is oxidized. In fact, at the beginning of this unit, we talked about how if you left an iron nail out overnight, it would react with oxygen in the air. It would be oxidized. That's because you go from neutral iron to an iron cation, picking up the oxygen anion. So oxidation and reduction reactions do exist, and we are going to really cover them when we talk about redox reactions as their own entity, because they are quite complicated.